Alright, in this video we're going to be running some path integrals and parameterizing curves. So we're going to start with this set of problems where it's like, hey, here's a curve, write an equation for it. Okay, so I'll just show them to you, then get to it. So the first one is a circle centered at the origin with radius 3. And it's got that counterclockwise orientation that we're used to, so we should be able to do this. Okay, so we've got this. We know that if this was 1, it would be cosine of t and sine of t. Okay, but it's going to be 3 times as big, so it would be 3 cosine t and 3 sine t. So also, and that'll have the right orientation. It'll go to the right spots. We just need to, kind of set some boundaries for the time so that it's only traced once. Okay, so that'll be 0 to 2 pi. The next one is an ellipse. It goes out 4 in the x direction and 3 in the y direction. So maybe I'll try it first. Right, so it's like, okay, and I don't know, maybe you went and looked up how to parameterize an ellipse on the internet, or maybe just see what it's going to be, but I can say r of t is going to be, okay, on the x direction, it's like a circle, except it's going to be 4 cosine t and 3 sine t as t runs from 0 to 2 pi. Okay, and I think I'll actually show you why that works also, in case you're like, oh, actually more. Try out. Okay, so the equation they gave us for the ellipse is x squared over 16, y squared over 9, together adds to 1. Okay. So that's going to be 16 cosine squared t when I square x. Plus, when I square 3 sine t, that'll be 9 sine squared t. And that's like saying cosine squared t plus sine squared t equals 1, which we know is true. Okay. Oh, whoops. This was 1b. One c is going to be, all right, it's a square. So it's going to be 3 here and 3 there. It's got this orientation here. Alright, so this one, there's not going to be like one equation that we can write that's going to trace out that. We're going to need to split it up into 4 different pieces and write a smooth parameterization for each piece, and that's why it's called a piecewise smooth parameterization. Okay, so I'm going to kind of call this part here C1, call this C2, C3, and C1. I think C1 will be easy enough. Okay, the x coordinate is increasing from 0 to 3, so I might just call that t, as t runs from 0 to 3. Y coordinate is always 0 the whole time, so like that. Okay, from 0 to 3. Then we're going to pick up C2 when t equals 3. Okay, so along this curve, x is 3 the whole time. And y is going to be increasing from 0 up to 3. But I can't just do t because, you know, t is going to start at 3, so that would be going 3 to 6, and that would be that line segment there. So what we need to do is I'm going to need to take t, and I'm going to need to offset it by 3. Okay. And because then when t is equal to 3, y will be 0. When t is equal to 6, y will be equal to 3, so it'll be right there. Okay, but if you wanted this to be equals and that to not be equals, or if you wanted both be equals, then again, I'm not going to care. It's the same thing. You're not saying that the curve is at 2 different places at one time. If we were to say that this was less than or equal to, just both of these things saying t equals 3 and at the point 3, 0. All right, so curve 3 is, okay, y is going to be 3 the whole time. And x is going to be starting at 3 and decreasing back to 0. So it's going to need to be something minus t, right? It's going to be decreasing. Okay, so this is going to be from 6 to 9. And let's see. Well, I would think it would be 3 minus t, but I need to offset by 3 or by 6, so it would be 3 minus t, which is starting at 6. Okay, and that works. Or you could call it 9 minus t, right? Because it's 6, it's 3, and at 9 it's 0. I'll just look at that and see why it's 9 minus t algebraically, or you know, in terms of the graph. Right, and then C4. Okay, x is 0 the whole time because I'm on the y-axis. And y is going to be decreasing from 3 to 0. So I would think 3 minus t, but I need to offset t by 9, so it would be 3 minus t minus 9. Okay, so that would be 12 minus t, I think, yeah, because when t is 9, I'm up here at y is 3, and then when t is 12, I'm back here at 0. So it'll be 12 minus t there. And that's piecewise smooth parametrization for that square. Alright, so now it's going to be along this line. It's going to go up to the point 5 and 4. And let's see, I'm going to go down and back over. Alright, so I'm just going to say that t is going to start at 0, and I'm going to deal with the line segment first. Okay, if it goes to the point where x is 5 and y is 4, that's like that line is y equals 4/5 of x. And you know, I think what I'm going to do is I'm just going to call x t and y 4/5 of t. So this will be my first piece of curve. C1 will be r of t is t and 4/5 of t. And, well, since x goes from 0 to 5 and t is x, I'm just going to let t go 0 to 5. And then the second piece, we're going to need to pick up at t equals 5 and go, I don't know, for a while. We'll figure out how far. I would think probably 4, because I'm going to go from y equals 4 to y equals 0 on a straight line. So I think I could let t run from 5 to 9. Okay, but the whole time x is going to be 5. And then it'll be 4, you would think 4 minus t, but I'm going to need to offset t by 5, so it'll be t minus 5. Yeah. Okay, and I'll have, alright, this in total is going to be 9 minus t. And the third part of the curve is along the x-axis, so that's going to be y is 0 the whole time and x is decreasing. So 3 r of t is going to be, all right, y is 0. And x starts over here at 5 and decreases, so you would think 5 minus t, but we're going to offset t by 9. Okay. And that's for t being between, so it would be 9 to 5, 14. And we'll want to check that for sure. But yeah, no. This will be 14 minus t. Because when t is 9, x will be 5, that's right there, and when t is 14, x will be 0 and y is 0, and so that'd be all the way back to where we started. Alright, so about like that. And this is where y equals the square root of x and y equals x. Okay. And we're going out to the point where x is 1 and y is 1. Alright. I'll do two different ones for this one. It's got two pieces, it'll be pretty easy. Okay. And it has, it has this orientation. So I'm going to start at the origin and do the curve first and then the line segment, but you could start out here and do the line segment and then the curve. It'll just be, I don't know, maybe a little more difficult. And right, for any given curve, there's going to be lots of different parameterizations. Okay, I'm just trying to do the most obvious one here. All right, so call that C1 and that's C2. So r of t, well, y is the square root of x, so maybe I'll call it t and the square root of t, as t runs from 0 to 1. And then we'd have, all right, well, y equals x, so I just got to figure out what it's going to be. Okay, so I think it's just going to be 1 minus t, as t runs from 1 to 2. Think about that. All right, y equals x, so I know it's got to look like that. Okay, when t is equal to 1, no, that's not it. Oh, I need to offset the time by 1, so it'd be like 1 minus t minus 1, so it'd be 2 minus t. Okay. So then when t is 1, I'm at the point 1, 1, and when t is 2, I'm at the point 0, 0, and y equals x the whole time, so that's going to be me along that curve. So, alright, and so yeah, we're happy with that. Alright, the last one. Is okay, this is y equals x squared, y equals 4, x equals 0. This orientation here. Alright, so it's going to start with the y equals x squared curve. Alright, so C1 is y equals x squared, so t and t squared. And this is when t is between 0 and 2, because x runs from 0 to 2. For C2, r is going to be equal to, all right, y is 4 the whole time, x starts at 2 and decreases, so I would think 2 minus t, but it's going to be 2 minus t minus 2, so it'd be 4 minus t, I think. And that would be 2 to 4. But it's always good to check, right? When I plug in 2, I get the point 2, 4. When I plug in the point, or t equals 4, I get 0, 4. And that would be, okay, going from here to there, whether y is 4 the whole time, that's going to be that line segment. And then C3 r is going to be equal to, okay, yeah, x is 0 the whole time, y starts at 4 and decreases, so I'd have 4 minus t, but I know I have to offset t by 4, so that'll be 8 minus t. And that'll be t running from 4 to 8. Okay, and that's all the parameterization principle I need to do today. Okay, the rest of them, I think oh no, I guess we'll have to do a little bit of parameterization later. Well, this one's going to be pretty robust. It's a lot of integrals. Okay, so we're going to work this one. And we know that x is 4t and y is 3t. T is running from 0 to 2. So I'm going to say that this is, okay, we've got that. We just need that ds piece, and that ds is the square root of x prime squared plus y prime squared dt. So that's going to be the square root of 4 squared plus 3 squared dt. Okay, so that's going to be just 5 dt. So I'm going to be integrating as t runs from 0 to 2, x minus y, ds is 5 dt. Okay, so that's going to be 1/2 t squared. Okay, and it's going to be half of 4 is 2 minus half of 0, so I've got 10. Let's see the next one. We're going to move on. So x is t, y is 2 minus t, ds is going to be the square root of positive 1 squared plus negative 1 squared dt, so it'll be square root of 2. And then I'll be integrating as t runs from 0 to 2, 4 times x times y times square root of 2 dt. Right, so I think we're going to distribute. So that's 8t minus 4t squared. And this is the type of integral we're good at running. I'm going to anti-differentiate. Plug in the bounds and subtract. Okay, that's 16 minus 4/3 of 8, 32/3, minus, when I plug in 0, I'll just get zeros, and that'll be the value of the integral. This one's going to be 3-dimensional, but it's not going to really work any differently, you'll find, I think. I'm just going to do the same thing I did. Find x, y, and z, and then dx. Okay, so this x is going to equal sine t, y equals cosine t, and z equals 8t, which means that ds is going to be the square root of dx dt squared. Well, dx dt is cosine t. Okay, plus dy dt squared is going to be negative sine of t. If I square that, I'll get positive sine squared t. Plus dz dt squared, so that would be 64 Interesting. But at the end of the day, cosine squared t plus sine squared t, that is 1. And so I'll have square root of 65 dt. So t is running from 0 to pi over 2. Okay. X squared plus y squared plus z squared is going to be okay, if I square z, I'll get 64t squared. Okay, and then ds is square root of 65 dt. Okay, so this is going to be 1 plus 64t squared. Squared dt. All right, I'm going to take an antiderivative. Okay. Plug in t equals 0 and t equals pi over 2. And I'll have a value. Okay, that's good. All right, this actually went more quickly than I expected. Okay. Wait, did I? Wait a second. I feel like I copied this problem wrong. Or, you know, like when I made the homework. Doesn't look right. Yeah, I definitely copied that wrong out of the textbook. So it was like 12t, 5t, and 3. So, all right. X is 12t, y equals 5t, z equals 3. All right, so this one, okay, ds is going to be the square root of 12 squared plus 5 squared plus 0 squared. That's a Pythagorean triple. It's going to be 13. Oops. Okay. And then my integral will become the integral from 0 to 2 of 8 times x times y times z. And then ds is 13 dt. And so I really think what I'm going to do is, now, you know, I'm going to have 2 total powers of t, so I'll hold on to that 3 to make my anti-differentiation a little easier, but I'll get rid of the 96 from the 12 times 8, the 5, and the 13. So this is going to be 96 from 12 times 8 and 65 from 5 times 13. I'll be left with the 3t squared dt, which is going to be 96 times 65 times, okay, t to the third, as t runs from 0 to 2, that'll be 8 minus 0, and, well, I don't know what that number is, that's too big. Too big for me to compute mentally. So. Alright, now the last one is we're going to keep evaluating the same path integral just over different paths, and I'm not sure this might be getting at something if they chose a different, certain type of integral along a certain path. I don't know. I think, oh, no, never mind, pardon me, that's something different that we're going to see soon. All right, C is the x-axis from x equals 0 to x equals 3. That's my curve. So I've got r of t equaling x is going to be t, and y is going to be 0 as t runs from 0 to 3. Okay, and, well, all right, I've got, let's see, oh yeah, x squared plus y squared, well, x is t. Maybe I'll actually actually write that in. The square root of 1 dt. And really what this is it's like a regular integral where we're integrating over the x-axis. And so since the line that we're integrating over it doesn't have any curvature at all and it's just parameterized very straightforwardly, you're not going to have that factor for your ds. Okay, I don't know, maybe that'll be something that'll become more apparent as you work more of these. So that's going to become the integral from 0 to 3. X squared plus y squared is t squared plus 0 squared. ds is dt. So that's 1/3 t to the third. This t runs from 0 to 3, and that's going to be 9, right? Because it's a third of 27 minus a third of 0. Okay, that was easy enough. Y-axis from y equals 1 to y equals 10. Right, maybe we're starting here, going up there. Okay, so this is going to be my curve C, which is r of t equaling, okay, x is 0, and y is going to be, I mean, I could say it's going to be t as t runs from 1 to 10. I might say it's t plus 1. Or 1 plus t. I think about it starts at 1 and then I add t for 9 units of time. 0 to 9, but if you wanted to let t run from 1 to 10 and it be 0t, it's going to be the same thing. Okay. And then I'll convert. Okay, ds is going to be the square root of 0 squared plus 1 squared dt. All right, and then I'm going to have, oh yeah, the integral from 0 to 9 of x squared plus y squared times the square root of 1 dt. And that'll be 1/3 of t plus 1 to the third as t runs from 0 to 9, which is going to be 1/3 of, okay, 9 plus 1 is 10 to the third, minus, when I plug in 0, I'll get 1 to the third. Oh, and that'll be 999 divided by 3. Okay, that's a whole number. Okay. And that was 6b. Keep going. All right, counterclockwise around the circle from 1, 0 to 0, 1. Okay, so this is the unit circle. So you know what that looks like. 1, 0 is right there. 0, 1 is over here. So it's the first quarter of the unit circle. So we know how to parameterize that. It's just going to be cosine t and sine t as t runs from 0 to pi over 2. Myself there for a second. Oh, yeah. So I need to convert x, y, and ds. That's fine. Okay, so the derivative of cosine of t with respect to t is negative sine t. I square that, I get positive sine squared t. Take dy dt and square it, and I'll get cosine squared t dt. This is another square root of 1 dt, so this is going to be integral from 0 to pi over 2 of x squared plus y squared. Well, x squared plus y squared is also equal to 1. And then ds is 1 dt, so Okay, we've done enough double integrals in this class to see that, okay, when I'm just integrating 1 dt, it's just going to be pi over 2 minus 0, which is going to be pi over 2. All right, then 6d is counterclockwise around a circle with radius 2. Kind of the same idea, though. Okay, so I'm going to start by parametrizing. Same exact thing from 2, 0 to 0, 2 along this circle. And so I'll say this is my curve C, which has equation R equals, it would be cosine t sine t, so it would be 2 cosine t, 2 sine t. T running from 0 to pi over 2. Okay, so I'll go in and convert my x's, y's, and ds's. So meaning that ds is going to be the square root of, okay, negative 2 sine t. I square that, I get positive 4 sine squared t. Take the derivative squared, I'll get 4 cosine squared t. And that's going to be the square root of 4 dt, which is going to be 2 dt. Okay. Then we will say, all right, the integral of x squared plus y squared is going to be 4 cosine squared t plus 4 sine squared t is just going to be 4. And then ds is 2 dt, so if I'm integrating 8 times the integral of 0 to pi over 2 of dt, well, that'll just be 8 times pi over 2. And yep, that's going to be all for this one. That was a good selection of beginning path integrals. We'll do a lot more in this class, and they will maybe be a little more interesting than these. But this was a good place to start, so thanks for watching.